All right, and as you can see kind of in this set of notes, what I'm trying to do is to show you examples of commonly given related rate types of problem. So far we've seen 3 examples that were basically geometry problems. Rectangles getting larger or smaller, triangles getting larger or smaller, circles getting larger or smaller, looking at volume, a lot of geometric type formulas. All right, so now we're going to look at, this is a classic problem that they like to give you, that you have a ladder that is leaning against the wall, and they're going to pull away the lower end of the ladder, and it's going to slide down the wall, okay? So they have 2 options with ladders, sliding down the wall or pulling it up the wall. Now I'm going to go get a little GIF to kind of show you what this looks like. All right, so here's a picture of a nice little ladder leaning against a wall. And what I want you to visualize when you're looking at this, there's kind of one little thing that's different about this one, is in the previous examples, our rectangle, our triangle, our circle, the dimensions of our geometric figures, everything was changing based on rates. The length, the width, the radius, the circumference, everything's changing over time. But if we take a look at the ladder problem, as we are pulling the ladder away from the wall, what you notice is that the height is definitely changing. The height is decreasing, okay, where the ladder is touching the wall. The length here horizontally is changing as well. Its leg, the horizontal leg, is getting larger as I move across. But what's happening to the hypotenuse, which is the ladder? That actually is a constant. So what's changing in this problem, this is where kind of what starts to get confusing for students, the legs are changing, but the hypotenuse is constant. Does everybody see that as the ladder is falling? All right. So when we are setting up this problem, the fact that they're giving me that I have a 10-foot ladder, this is going to be information that you need to pay attention to, because this 10-foot ladder is a constant. The ladder is not going to change its dimensions. That's not a variable in the problem. So you're going to have to kind of pay attention to that. All right. We are given some rates, so let's kind of read through. We have the lower end of the ladder is pulled away from the wall at a rate of 2 feet per second. So that's changing the horizontal leg of the triangle. And then when the lower ladder is 6 feet away, so there's my when. And then they have different questions. They're asking for how fast is the ladder sliding down the wall. So classic related rate problem. I'm being given a rate and some information and a when, and I'm trying to figure out how fast. So let's do A together. Let's kind of show how this is working. So I want to know how fast the ladder is sliding down the wall. So we may want to visualize this. Let's do a little picture here. Here's my wall. Here's the floor. Here's your ladder that was sliding away, and I am going to put 10 feet here. See how this is different than before? This is not a variable. That 10 feet is constant for the whole thing, so I'm going to put 10 feet there. The end of the ladder being pulled away, okay, I'm going to call this distance x because that's varying. I'm going to call this distance y because that was varying too. Okay, so I draw this picture in. I've got the picture of what's going on. I see what's varying. I want to know how fast the ladder is sliding down the wall. What quantity are we looking at? We're looking at this quantity over here, the y I have labeled in my picture. So y is going to be the height between floor and ladder top. You know, give it some type of a name. We're going to be measuring that in feet, and what I'm looking for is dy dt. That's what I'm trying to find. Okay, what am I given? X is going to be your horizontal distance between wall and ladder base, and again I'm measuring that in feet. I'm given a rate for that one, so I know dx dt is 2 feet per second, and it's pulling away from the wall, and as I pull away from the wall it gets bigger, so it's positive, it increases, so that's positive 2 feet per second. Okay, so the quantity and what I'm looking for, which rate, the quantity and the rate that I am given. The when is when x equals 6 feet. All right? And then we come up with our quantity equation, or quantity formula. We have this information. If you just take a look at it, like, oh, wait a minute, that's Pythagorean theorem. X squared plus y squared equals 100. This is why you need this, because this is not a variable. This was set for the problem. Then I get my related rates equation. I take the derivative of my quantity equation with respect to time, and we end up with a related rate equation of 2x dx dt plus 2y dy dt equals 0. We are trying to find dy dt, and so I basically have to take the related rates formula and plug in everything I know. Now, we're going to have some things that we're missing, so I start filling it in. I'm like, okay, 2. The x was 6. dx dt was 2 plus 2. And then I get to this y, and I'm going to put a star there. I'm going to have to find that in this problem. So we're like, okay, how do I find the y? What do we know? Now we go back to the instant. I know a relationship using the quantity equation. I know that x squared plus y squared equals 100. Can I find the y when x is 6? Sure. 6 squared plus y squared equals 100. 36 plus y squared equals 100. Y squared equals 64, so y equals 8. At that instant, when, because this is the when part, I needed to find an information. So I find it, I'm going to plug in my 8, and now I simply have to solve the problem. You end up with your dy dt, and I'll leave you to verify the arithmetic for that, but you should end up with -3/2 feet per second. Now, does it make sense to us that this is a negative value when I'm looking at it? And hopefully the answer is, yeah, that makes sense, because what's happening is y is decreasing. The ladder is sliding down the wall, so the height between the top of the ladder and the floor should be a decreasing rate. So we answer the question for A. When the base is 6 feet from the wall, the ladder is sliding, let's do down, so I don't have to, sliding down the wall at 1.5 feet per second. There we go. We've answered the question for A. All right, now let's take a look at scenario number 2. So now let's look at B. B, same problem, except now I want to know how fast the angle between the ground and the ladder is changing. How fast the angle, so theta, we're going to make that the angle of elevation, measured in radians, because everything in calculus is going to be measured in radians when we do this. The angle of elevation in radians, and what are we looking for? We're trying to find d theta dt. So our variables, we still have x, y, 10, and theta. So now our job, we want to find a quantity formula, and we want to find a quantity formula that relates theta to some of the information that we already have. And I would probably try not to use like the y, because you're given a rate that is about x. So I would probably try to do theta and x together. And so I keep looking at that and I think, what do I know? What prior class might give me some information, like trig? What do I know about an angle, its adjacent leg, and its hypotenuse. Oh, wait a minute, that is a cosine ratio. So my quantity formula, cosine of this angle theta, is x over 10. There's nothing wrong with saying, hey, I'm going to have some trig involved in this. You look at the variables you have and how can you relate those variables together. We're going to use some trig in this one. So it's not a geometry problem, it's now a trig problem. All right, so then we go on. We want to get our related rates formula. So our related rates formula, we're going to take the derivative of cosine of theta with respect to t. We're going to take the derivative of x over 10 with respect to t. So our related rates formula, the derivative of cosine is negative sine theta, and then don't forget your d theta dt. And then the derivative of x over 10, or 1/10 x, would be 1/10 dx dt. So here is my related rates formula. And that's what we're going to plug our information in. Now, as I go to plug things in, what am I looking for? I'm looking for d theta dt. dx dt I have. All right, so let's start filling in d theta dt. 1/10 dx dt was sliding at, I wrote it down, I have to look back up here. dx dt was 2. Okay, and I have a negative, and then I need this, oh, sine theta. I don't have sine theta. Can I find sine theta at that instant? Yes. So I'm going to come over here on the side. I'm going to bring my triangle down that we were working with. At that instant, we have theta, we have 10, we have 6, because now we're in the instant. We're trying to when x is 6. So x is 6. And remember, we already did work in A. We know that at that instant, y was 8. So that's an 8. So what is the sine of theta given our little right triangle? Opposite over hypotenuse, 8/10 or 4/5. So I do the work to find whatever I'm missing. Here's my 4/5. And then I simply have to solve for d theta dt. And d theta dt equals negative 1/4. I will leave you to do the problem. And my units are radians per second. And then I can answer the question and finish out B. The angle, okay, so when the ladder is 6 feet from the wall, the angle is decreasing at 1/4 of a radian per second. And then we're done with that problem. So in this one, kind of what we're doing now in looking at it is, instead of doing geometry type application problems, once we write down our quantity and rate we're looking for, our quantity and our rate that we're given, that sometimes the quantity formula that you come up with requires you to have trigonometry knowledge. That I had a Pythagorean theorem relationship up here in A, which was sort of still technically geometry, but in B I had to use a trig relationship in order to get my quantity formula. That's why related rate problems can be hard, is because for you to come up with the quantity formula, you have to have prior knowledge from prior math classes. And you also have to have prior knowledge of how to find pieces of information. Like, oh, I had to know that in order to find the sine, I have to draw the triangle, get the sides, and do opposite over hypotenuse. That's what makes these problems hard. All right, let's take a look at the C and D. So I'm going to flip over to the next page. I did give you 2 pages in here to do this. So we're now doing C. How fast is the area changing? Okay, I'm just going to bring my picture back in from the previous page with my ladder. That was 10, x, and y. I'm not going to worry about theta for this problem because I'm doing area. So for C, I'm going to have a quantity of area, which is going to be in feet squared. I'm going to be looking for dA dt. My variables, the x, the 10, and the y, so I'm probably going to go ahead and find the area equation using x and y. So it'd be area is 1/2 equals base times height. Now, I'm going to use a method that we used in the previous one, which is if you can make your quantity formula, instead of having two variables, having it be in one, that's probably going to be easier. So I'm going to remember that in this problem, I did have a relationship between x and y. X squared plus y squared was equal to 10. Y squared was equal to 100. 100 minus x squared, and y, because it's a distance, would be the square root of 100 minus x squared. So I'm going to go ahead and just use the method where I'm going to make this, instead of doing two problems, I'll probably actually show you both ways, but I'm going to show you this method first. Option 1, I'm going to make my quantity formula area equals 1/2 x, and then 100 minus x squared to the 1/2. And so that way I only have one variable to take the derivative of when I do this. All right, so then we find my related rates. I'm going to take the derivative of a with respect to t. I'm going to take the derivative of 1/2 x, 100 minus x squared to the 1/2 with respect to t. So dA dt equals, now I'm going to have to use product rule. So first times derivative of the second, 1/2, 100 minus x squared, negative 1/2, chain rule, negative 2x, chain rule, dx dt, okay, plus the second, 100 minus x squared to the 1/2 times the derivative of the first, 1/2, dx dt. Now the nice thing about this is we don't have to simplify. I would just start plugging and chugging at this point. And the nice thing about this is I have everything I need. Here's my related rates formula. And then we're just going to plug in everything we know. I'm trying to find dA dt. Plug in everything we know. dA dt equals, the x was the when, 6. And I have this 1/2, 100 minus 6 squared to the negative 1/2. Then you have negative 2 times 6, dx dt. Our dx dt was, dx dt, 2 feet per second, 2, plus my 100 minus 6 squared to the 1/2 times 1/2 times my dx dt, which is 2. So plug everything in, and then from that point we just have arithmetic in order to calculate our dA dt. I am going to leave this to you to verify, and you would end up with 7/2 feet squared per second. All right, so that's option 1. And to be honest, you're going to be like, well, this option actually is going to end up being longer this time. But if I had not done A and B already, if this was the problem and I was coming straight into it, I am probably going to go with this option because I like to have one variable. All right, option 2, just to kind of contrast what might be happening here in part C, instead of eliminating that y out, I'm going to leave my quantity equation as 1/2 xy. And if I leave that, I'm going to take the derivative to get my related rate equation. Okay, which doesn't bother me too much when I go to do my formula. So we have dA dt equals 1/2 x dy dt plus y times 1/2 dx dt. And so this would give me my related rates formula, and I'm going to start plugging things in. And here's kind of why this could be difficult or challenging if this was where I had started. Here's what I'm looking for, dA dt. I have 1/2, my time 6, my dy dt. Now, if I have not done parts A and B, this would need to be calculated. Okay, plus the y That would have to be calculated. And then our 1/2 and our dx dt was 2. So when we're looking at this, these two pieces of information are going to have to be calculated. Now, lucky for us, this ends up being an easier option because I already did this. This was done back in part A. There's my y, 8. Okay, so we'll put a little star by that. We're going to import that in. And I actually found dy dt as well, my -3/2. So because I did this in A, I'm good to go. If I had not done this, like if this was the actual beginning of the problem, you would have to do all the work from A at this point in order to calculate that. But since we already did it, I'm just going to import it and then use that to get my answer. So because I already did part A, part C is easy and easier using option 2. But if I had not done part A, that would have been a lot of extra work to calculate this versus up here where I already had the information I was given. Again, you're going to have options. You're going to decide which way you like best or which information you have in order to do it. And you should end up with the same answer that we had before, which is 7/2 feet squared per second. And then we will answer the question, which is when the ladder is 6 feet from the wall, the area is increasing at 7/2 feet squared per second. Okay, so just kind of trying to show you all the different options that you're going to have. All right, so now we're looking at part D and kind of seeing what's going on with this one. What new interesting thing have we added? And part D is asking you for the acceleration of the ladder down the wall. And you might be tempted to be like, well, what are they asking me to do here? But you have to remember, acceleration is a rate. It is the rate of a rate. It is a second derivative. Okay? So in part D, when we're talking about acceleration, acceleration is the change second derivative of what? It's the rate that the height is changing over time, and you have to take the rate of the rate. So you kind of have to go, the quantity I'm still interested in is y, okay? The height, the vertical distance between your ladder and the floor. That's my quantity, it's my variable. But what I'm actually looking for is the second derivative of y with respect to t. That's what we're looking for. So in this problem, you're like, what are my variables? How am I supposed to find acceleration? Where you're still having your variables is your x, which is your horizontal distance, your dx dt, which was your 2 feet per second, and the quantity equation that you're going to start with is actually the same one we started with in A, because I'm trying to relate x and y. Okay, so the only difference is I don't want to look at the first derivative. I want to look at the second derivative so I can relate the accelerations together. So let's take a look at this and see what happens. We had our quantity formula. Our x squared plus y squared equals 100. We already did our related rates formula, okay, which was our 2x dx dt plus 2y dy dt equal to 0, just bringing that from the previous page. Okay. Now remember that what I'm trying to do, and this is where we're just going to need a little work, we're trying to find the second derivative. And so what I have here is your first derivative. And so I'm going to need to take the derivative again. Now I am going to say it's probably better for you to go ahead and let's solve for dy dt, because that's going to make it easier in order to do the second derivative. So I'm just going to move things over. So 2y dy dt equals negative 2x dx dt, and then your dy dt equals negative 2x dx dt over 2y, and I'm going to cancel those 2's out, so it's negative x dx dt over y. So I'm going to solve that over, mostly because it's easier to take your second derivative, okay, your second derivative in this notation. So I'm going to take the second derivative, the acceleration formula. Going to the next thing, I had the quantity, then I have my velocities, my rates, now I'm going to my acceleration. I'm going to take the derivative of dy dt with respect to t, which means we're going to take the derivative of this negative x dx dt over y with respect to t. And then we're going to use a little bit of our quotient rule. Okay, so, and product rule, because we have that up there. Let's do our low d high, the derivative of the top, negative x, second derivative of x with respect to t, plus dx dt times derivative of negative x, which is negative 1 dx dt. Okay. All over, so that was low d high minus high, so plus d low dy dt all over low squared y squared. So that gets us to where we have our derivative. And we're like, man, that is some complicated formula. Now, the question is, we're going to have to plug in all of this stuff. Now, I'm going to kind of come back to this and like, there's got to be an easier way, because now I'm going to have to calculate, okay, up here, what's basically going to happen when I have my second derivative, my acceleration for my x. Alright, so basically we get this all out, now we have to fill in everything that we need. So kind of filling it in, we have our y, which we already figured out, when x is 6 is 8. Then we have our x, which was 6. Now we need the derivative, second derivative of x. But now think about this. We had x and dx dt was 6. Or sorry, dx dt was 2, which is a constant. What's the derivative of a constant? 0. The velocity, the rate, was constant for the x, so therefore its acceleration is 0, so we add that in. All right, plus our negative 1 times our dx dt, which was 2, so we put that in, times our negative 1 times our dx dt. Whoops. Hold on once, I got to figure out where I am in the formula, filling it in. So negative 1 times our 2 plus my x, which was, close your parentheses, 6, dx dt, 2, dy dt, which was a negative 3 halves from a, all over y squared, 8 squared. So we had everything, we plug it in. I'll leave you to do the arithmetic. You get negative 25 over 32 feet per second squared. Now, kind of as a comment, there is a little bit easier way for this. When I find this part right here, before I actually take the derivative, remember the whole make it easier type thing? When we are doing this problem, we had dy dt equal negative x over y, and then you had, of course, times that dx dt. For this problem, dx dt was constant. It was 2. It's not going to change no matter what we're doing in the problem. It's always 2. So to make this an easier problem, what we could have done is plug in the 2 here, because it was a constant rate for the entire problem, and then that makes our derivative a little easier. So now when I take the derivative with respect to t of both sides, I get the second derivative of y with respect to t squared. And I still have to use quotient rule, but that's a constant. That makes it a little easier. Low d high minus high, so it ends up being plus d low all over low squared. So this derivative is preferable to that one because it had less information because we had a constant rate of change. But you'll notice you get the same answer. You plug in your 8, your -2, your 2, your 2 times your 6 times your -3 halves all over your 8 squared, and it works out to be exactly the same thing. So I just wanted to make a comment about that if you have a constant rate of change, remember the simplify early and often, if you can substitute something in to make it a little easier, you want to do that. Now let's see, what did they actually ask me? What is the acceleration of the ladder down the wall? So when the ladder is 6 feet away, the acceleration, remember this is the acceleration you're finding, okay? That's the speed, that's the change in the velocity. So the rate the ladder is falling, because remember you got to go back to the previous one. When I'm talking about the rate of change, I talk about the quantity. When I'm talking about acceleration, I talk about the velocity. So the rate the ladder is falling is decreasing at 25 over 32 feet per second squared. Okay, and so that is the final version of that. So that is a good kind of overview of the typical ladder problem.